Yes, again. Yeah. Okay. Great. So the title of my talk today is Disciplined Nonlinear Programming. This is essentially, yeah. So this talk is essentially about a new feature in CVXPY which allows you to formulate and solve, to some extent, nonlinear programs. And this is joint work with William Sang, Park Noble, and Stephen Paul. And if you know about linear programming, you should be a bit skeptical about this word discipline. Because typically in nonlinear programming, in modern languages for nonlinear programming, you are allowed to formulate a problem in any way you like, that you then pass it off to a solver, and you hope that the solver will be able to compute a solution, whatever that means. But what we will see is that in this CVXPY extension of nonlinear programming, there are some rules you must follow. There is some kind of discipline. And one of the goals today is to argue why it makes sense to enforce these simple rules. But before we talk about that, I want to say a few words about convex optimization. So here we have a generic convex optimization problem, and I think it's useful to sometimes take a step back and ask, why do we care about convexity? Well, the classic academic answer is that convexity is great because, for any convex problem, a local solution is also a global solution. That's the academic. But there's also another more modern and pragmatic answer, namely that convex optimization is great because we have very reliable software tools, which makes convex optimization actionable. And I shared this opinion that this is what makes convex optimization great with a professor in Sweden who's pretty old, and he got furious. He said, "How can you dedicate the beauty of convex optimization to software and not the theory?" And I knew that I wouldn't be able to convince him. So instead, I started asking simple questions. So I asked him, okay, but 45 years ago, when you were a PhD student, did you care about convex optimization then? And he said, no, I cared more about linear programming versus nonlinear programming. Because you see, young kid, back then, we had some kind of software for solving LPs that was actually, doable for experts. But solving something else than LPs was much more difficult because there was, no good software. And then I asked him, after that response, I asked him, okay, so do you care about convex optimization today? And he said, yeah, because we have software, so it's actionable. And at that point, he realized that he was caught by my trap. He had argued against it. So I really think this is, a modern and realistic answer. So one of the reasons why we have a great reliable software for convex optimization is this notion of disciplined convex programming. So disciplined convex programming is the mathematical framework that CVXPY and other modern languages implement to verify convexity. And what is quite interesting is that classic commercial software like Ampel, I first learned optimization using Ampel. They don't implement disciplined convex programming. So it's a bit unclear how they actually verify convexity. Yeah. Yeah. Thank you. Yeah. Yeah. Like this. Yeah. Yes. So I think this is quite interesting. If someone actually knows how Ampel and GAMS and those type of languages actually verify convexity, I would be happy to hear that. So if we think about disciplined convex programming modern languages like CVXPY, what do they actually do? Well, they have two main tasks. They have one analysis task, in which they verify that the user-specified problem follows the rules that this framework enforces. So it essentially verifies that the problem the user tries to solve is convex. That's the analysis step. Then there is also a synthesis step, in which the modeling language takes the high-level problem description and transforms it onto a form that a numerical solver can understand. And exactly what this numerical form that the solver uses is not really important for its solver. But something I want to emphasize is that there is very little communication between the modeling language and the solver. Because once the modeling language has formed this standard form, it takes the data that defines the standard form, passes it to the solver, and the solver then knows everything it needs to know to solve the problem. And the reason why I mention this is because later in nonlinear programming, we will see that the modeling language plays a bigger role in some sense. We will see that there is communication between the modeling language and the solver in every iteration. So if the modeling language is slow, then it will be the bottleneck and not the solver. That's something we want to avoid. So finally, I want to say a few words about what to do when your problem is not convex. So here at Stanford, we teach a class in convex optimization, where we kind of give the impression that most problems are convex, and there are some non-convex problems, but we can always convexify them using certain tricks. That is not true. Like, the world is non-convex, but once you start looking for these tricks, you realize that there are certain classic problem families which are non-convex, but they become convex after some trick. So one of these tricks is, for example, you can do a change of variables. So one classic example of this is if you want to do maximum likelihood estimation of the parameters of an exponential family. That maximum likelihood estimation problem is non-convex, but if you make a change of variable to something called the natural parameters of the exponential family, you get a convex problem in those new variables. And there are several other canonical examples of when this is possible. So if you encounter a problem that is non-convex, this is ideal. This is what we should try first, to convexify it using a change of variable, for example. The second thing you can try to do is to stare at your problem and see if it has some convex structure, because then you can implement heuristics based on convex optimization. So, if it is just one constraint in your problem that causes the non-convexity, maybe you can linearize it, solve a convex subproblem, and do that several times. So there are several different methods that fall into this category, which are very related. But then we have something that to the CVXPY community is, a new and unknown feature. Namely that, why don't we just ignore all the convex structure in the problem? I'm glad Stephen Boyd is here, because he wouldn't like that comment. Why don't we just apply a general purpose nonlinear programming solver? So this is what we will focus on for the rest. So here we have a generic nonlinear program. We don't assume necessarily that these constraints, equality constraints, are affine. So we don't make any assumptions on the problem at all at this point. We make one assumption, though, namely that in linear programming, we typically assume that the objective function and constraints are differentiable. That's typically a necessary assumption. So this abstract form of a nonlinear program is very generic and includes, essentially any problem you can think of. So in particular, it includes many empty hard problems. And that's a hint that as soon as we unleash nonlinear programming, we don't have as strong guarantees as in the convex optimization world. And convex optimization, to some extent, it just works. You don't have to tune a parameter. You don't need to babysit the solver. But here in the nonlinear programming world, that might not apply, because how successful you are can depend on where you initialize your algorithm. That's very important. How you formulate the problem. Two different formulations can be differently good. One can be solvable and the other can be impossible to solve. And also, of course, the choice of algorithm. So if nonlinear programming is so general, what can we actually expect? Do we have any theoretical properties? Well, as I mentioned, this problem class includes NP-hard problem. So it is unrealistic to expect convergence for global minimas. Most people know. So what they say instead is that, oh yeah, sure, we don't have convergence for global minimas, but that doesn't matter. We will always converge to local minima. But that's actually a myth. Because nonlinear programming solvers, they might even fail to find a local minima. So they can actually even converge to a non-physical point, even if the problem is physical. So what do actually nonlinear programming solvers guarantee? Well, under some assumptions, they at best guarantee convergence of points satisfying the KKT conditions. So these KKT points, well, they can be local minimizers, which are good KKT points. But they can also be bad KKT points. They can be local maximas or saddle points. But of course, we don't want to converge to a local maximizer. We don't want to converge to a saddle point. So these solvers for nonlinear programming, they implement different heuristics that steer away from undesirable KKT points. But of course, we can't really prove that they will converge to local minimas. And the convergence guarantees that actually exist for nonlinear programming, they assume something called constraint qualifications. And we are not going to talk that much about constraint qualifications, but what I want to say is that when I started working on this project, I was under the impression that constraint qualifications is not really important in nonlinear programming. I thought that it's this topic that people invented to write papers. But after playing around with many solvers and different problems and see when solvers actually fail, I have changed my mind. I now think that this common constraint qualification, which is called LICQ, is important in practice in the nonlinear programming. Maybe someone else has another opinion, so I would be happy to hear that later. But I guess theoretical mathematicians can be happy, because something they write papers on actually is important in practice. So when you look at these theoretical guarantees, it looks like a pretty sad story, at least compared to the convex optimization story, where it just works. So I want to emphasize that this is theory. In practice, my experience is that these nonlinear programming solvers, in particular IPO, which I'm going to talk about, works very well in many cases, in particular if you provide it with a good initial form. So there's a gap between theory and practice. So suppose you want to apply nonlinear programming. What can you do? Well, there are several modeling languages that support nonlinear programming. For example, YALMIP, JAM, Pyomo, and Casari, which are free and open source. I'm not sure if Pyomo is open source, but it's free at least. It is? Okay, I do. And then you also have commercial software that also support nonlinear programming. And if we look back at the convex optimization case, in convex optimization, the modeling language has one main task, essentially, to canonicalize a problem, to transform it onto a form that the solver can understand. And when that is done, there's really no further communication between the modeling language and the solver. But here in nonlinear programming, the task is different on the modeling language. So the main task of the modeling language in nonlinear programming is to provide the solvers with oracles for evaluating gradients and Hessian. And this must be done in every iteration. So that is why there is communication between the modeling language and the solver. So, if the modeling language is slow on computing derivatives, doesn't take sparsity into account, doesn't matter how good your solver is. And this is something we ran into issues with. So, now we have these modeling languages, which are great. They are fantastic pieces of software. Yalmit was actually invented at the university where I did my undergrad in Sweden, so pretty cool. Back then, I didn't know what optimization was, so I never, appreciated and said hi to that professor, but I secretly admire him. So we have these fantastic pieces of software. Why do we need another model? And I asked myself that question when I started working on this project, because you don't want to do unnecessary work. And so I played around with all of these four, and I realized that they are extremely good if you know what you're doing. But if you're tired when you formulate a problem, or if you are not super knowledgeable in optimization, these modeling languages, they won't save you really. They might pass a formulation to the solver that is impossible for the solver to solve. This sounds very abstract, but to make it more concrete, we have a very simple example here where many with existing modeling languages I have tried failed. So this is just a convex optimization problem. It's a lasso problem, and since it is convex, we expect that it should be easy to solve. And this problem is convex, so of course we should use convex optimization software for it. But let's pretend for a moment that we actually use nonlinear programming. What happens? So the second term here encourages sparsity. So we expect that at the optimal solution, some of the components of x will be 0. So at the solution, the objective function is non-differentiable. But what the existing modeling languages do is that they ignore non-differentiability. They say that, okay, we have an objective function. It's differentiable everywhere in the space, except for some points. What the mathematicians say. The set, it's almost everywhere differentiable. But, and then they just pretend that, yeah, it's fine. We can just pretend that it's differentiable everywhere. But that doesn't work necessarily, because here we are interested. Like, we expect the solution to occur at a point of non-differentiability. And so if you ignore the non-differentiability and just provide oracles that evaluate the derivatives of this, the solvers can actually fail. So here is the output from IPOpt. IPOpt is probably the best nonlinear programming open source solver out there, and we interface it using Casade, which is a very famous nonlinear programming model. So this is a problem with like 10 variables. It's a super toy problem, and we look, and yeah, okay, it seems to converge in 13 iterations. That's great, but then you look closer, then you realize that the minimal objective value is 100 billion, maybe, something like that, which is probably not the optimal solution. And if you look even closer, you see that IPOpt actually crashed. So when you see this, should we blame IPOpt, the solver, or the modeling? I think most people, when they see this, they blame IPOpt, because obviously it's IPOpt that crashes. But we should blame Casade. We should blame the modeling language, because it hands IPOpt a problem formulation that it doesn't support. So that brings us to discipline nonlinear programming. So discipline nonlinear programming is a new mathematical framework or grammar for specifying nonlinear programming. So in this framework, we distinguish between two types of functions, smooth and non-smooth. And if you have smooth functions, they can appear any way you like. But there are certain rules governing how non-smooth functions can appear in your problem. So, if all your functions are twice continuously differentiable, then there are no rules. It satisfies the DNLP rule set. And for the purpose of this talk, when there are several different definitions of smoothness depending on who you are talking with, but in this talk, when we say smooth, what we mean is we mean an atom or a function that is twice continuously differentiable in the interior of its domain. So I'm going to tell you at a high level what rules you must follow for CVXPY to accept your problem. But I think it's very important to emphasize, what do you actually gain from following our framework? If you follow our framework, do we guarantee that you will find a global minimum? No. Do we guarantee you that we will find a local minimum? No. Do we guarantee you, anything more than other models? No. We don't make any promises. What exactly do we guarantee? We guarantee that if you follow our rules, we can take your problem and transform it to an equivalent form that only involves smooth functions, which solvers like. And we can also guarantee that the transformations we make, they are not bad in the sense that they violate this constraint quantification called LICQ. So that's what we guarantee you if you follow our rules. In practice, if you plug this problem into our framework, IPOP solves it gracefully, 9 equations. So at least we have one problem where we are better. But my experience, I'm a bit biased, but I really think this makes a difference in practice. So let's look at what type of rules you must follow. So as usual in CVXPY and discipline convex programming, you construct problems using atoms. And we divide atoms into 3 categories: smooth, non-smooth convex, and non-smooth concave. So discipline nonlinear programming has its own rule set, which defines which specify what rules must follow. But they are very similar to the discipline convex programming rule set. If you just change a couple of words, you get the same thing. And I think at least some people in here know the discipline convex programming rules that you must follow. So instead of presenting and defining our new rule set from scratch, there's a very, very neat characterization in terms of discipline convex programming rules. And essentially, it is summarizing one line. So if you take your problem, then you should check. You look at all the smooth atoms and non-smooth atoms. And you take the non-smooth atoms and you just pretend they are atoms. If you do that, you pretend that smooth atoms are affine, then you check the DCP rules. If the DCP rules are satisfied, well, then your problem is DNLP. So if you know the DCP rules, you know discipline nonlinear. So it's very, very simple in some sense. Yeah. So now in CVXPY, there are some new atoms which haven't been available. For example, you can multiply 2 variables. That's a smooth atom. In the quadratic form, we no longer assume that Q is a positive semi-definite or negative semi-definite matrix. It can be indefinite. And something which is completely new is trigonometric functions. You can optimize over them now in this extension of CVXPY. And all these atoms, they are not convex or concave, so they haven't been available in CVXPY before, but they are smooth. So now they are available. So I'm not going to talk that much about what we do under the hood, but at a high level, we take your problem and we convert any non-smooth things you have into smooth formulations. So how do we actually do that? Well, it turns out that if you follow our rules, you can show that the problem you specify is equivalent to a problem in which the non-smooth functions appear in a very specific way. So we can guarantee that we can find an equivalent problem in which a non-smooth convex atom appears in an epigraph constraint. And if you had a non-smooth concave atom, then we can guarantee to find an equivalent problem in which it appears as a hypergraph constraint. And now it is very well known how to convert these into smooth formulations. So, for example, the epigraph of the absolute value of x is just two linear inequalities. And these transformations we do, they are very similar to the ones CVXPY already. So when I told my mother like what I'm doing for work, I guess, I showed her this slide because she knows some basic calculus from high school, and I told her that we have automatically reformulated that and that. She was like, "What? Is that what we have been paying you money for 18 years for?" And it is a fair question, but it is nice to automate it because doing it yourself is very error prone. And in particular, everyone can do this rewriting, but there are more complicated atoms like the Huber function. Like formulating the epigraph of this is not as obvious. And this is actually, but then my mother said, "Oh, but what do you mean? This is a smooth function." That is not according to our definition. Because here, where the Huber function goes from quadratic to linear, it's not twice differentiable. That's why we must do something. We must reformulate it exactly that smooth way. So now I just want to show you some examples. But I think what you should remember about discipline nonlinear programming is that if you know discipline convex programming, it takes 3 minutes to learn this new extension. If you don't know discipline convex programming, it might take 15 minutes to learn the extension. So it's still I think it's easy to learn and it's perfect for students to learn. So now I just want to show you some examples. So we have this DNLP extension of CVXPY. It's a fork of CVXPY right now. So we support a couple of open source solvers. Of these, I would personally recommend IPOpt. That's one I have most experience with, and it seems to work great for all the problems I have tried, if you formulate your problem in the right way, which we do for you, basically. And we also support some commercial solvers. We have some plans to integrate it in the future in CVXPY. So right now it's a separate package you can download, but hopefully it will be available eventually. So I'm just going to show you some toy example to show you what you can do. So our first example is in circle packing. So here the goal is you have n circles and you want to pack them into a small square. You don't want them to overlap. So the objective function here is a proxy for that we want the smallest box. The constraints say that two circles are not allowed to overlap. So when you see this problem and you start parsing, well, you might realize that the objective function is convex. Like, yeah, I think it is. But you look at the constraints and you see that, well, here we have a convex function. This is like we should be outside a ball. That's very non-convex. But so this does not satisfy the discipline convex programming rules, but is it DNLP friendly? And it actually is. Because you take this problem, you find smooth atoms, the smooth function, which is just this norm, the norm squared. And you think that it's affine. So we have something affine greater than. Well, that's a convex constraint in DCT. So this is a discipline nonlinear program. So to solve this, you can just use standard CVXPY syntax. And if you do this for 10 circles, you find with different radiuses, you find this configuration. And we see that, well, they don't overlap, and it seems like they are pretty packed. But remember that in non-convex optimization, it might matter a lot where you initialize the algorithm. So it makes sense to run this, for many initial points. If you have the compute budget, like this problem, it's 0.1 seconds to solve, so we can do it. So do you need to implement like a for loop yourself? No. We actually have a feature, so you can specify a flag to the solve command, which is best of equals 500 in this case. So what this means is that we solve your problem 500 times, and we just return best solution found. So if you do this, you actually find a better packing. This is tighter. And here is the distribution of all the solutions we find. Coverage is just how much of a square we cover. So we like high numbers. So we see that the best configuration is here. It's this one. It has 77% coverage. Sometimes you are very unlucky and find a solution with coverage 60%. And then I just want to show you one more example. So in this example, we are trying to recover a sparse signal, and we assume that we have measured it through a compressed sampling matrix A. So we have some measurements of it, and we want to recover. And we assume that this signal that we are recovering is, pretty sparse. So a typical approach is to minimize the L1 norm, subject to the measurements we have taken. That's a convex approach. But what we do here is that we want something even sparser. So we use a square root of absolute value. And if you draw that function, L1 norm looks like that. This function looks like even sharper. So this objective function promotes sparsity even stronger, even more aggressively than an L1 norm. And you can parse this problem. So the square root here is a smooth atom in our world, because it is twice continuously differentiable in the interior of its domain. So if you just treat the square root as affine, well, then you have something affine of the absolute value, that's convex. So this, if you do that, then it satisfies the DCT rules, so it is actually DNLP. And if you compare the recovery of this non-convex approach, is on the left side, and here on the right side, we have the convex approach, which minimizes the L1 norm instead. Here on the x-axis, we have the cardinality of the signal, and here on the y-axis, we have the number of measurements we made. So we like points that are yellow, because that means that we recover the signal 100% of the time. And we see that this non-convex approach is actually better, because its phase shift, where it starts to fail, occurs later than the corresponding convex approach. Yeah, okay. So that's everything I was planning to say. I'm happy to take questions. If we don't have time, I'm happy to take questions later.
So I'm sure Daniel will be happy to answer questions after we finish. And